Okay, hi Year 12. Today we're going to have a look at 1H, the limiting sum of a geometric series. What that means is the sum of the geometric series that we're looking at could have two different kinds of sums. It could have a sum that gets extremely large, or it could have a sum that reaches a limit that is a value, and that's the one that we're going to have a look at today. So before we have a look at our notes here, what I'm going to have a look at is just to talk you through a series. So this bit's not in your notes. This is some other bits of information, but we'll talk you through that. So it says in some geometric series, the sum becomes very large as n increases. So if you have a look at the series we've got here, okay, and we're increasing by a ratio of 2, as our terms increase, our values here are going to increase. So if we were to sum this series, it would be enormous if we were going towards n going to infinity. So we would say this series diverges, or it has an infinite sum. In some geometric series, the sum does not increase greatly after a few terms, and we say this series converges and has a limiting sum. And that's the kind of series we want to have a look at today. And that would be something similar to down here. So we're starting with 2, and in each movement along our terms, we're halving our series. So what we're going to find is that as we move along and our terms increase, the size of the term that we're actually adding on is going to be so small that as we get towards infinity in the number of terms, the sum doesn't change very much. So we might be only adding on, for example, 0.000000001 from one term to the next. So the sum wouldn't change very much. And that's the kind of series we want to have a look at today, and that's going to give us a limiting sum. Our notes today, we'll look at the theory and then we'll have a look at some examples. If we continue adding additional terms to the geometric series, the outcome depends on the size of the ratio r. And that was what was happening in the two series that I showed you before. The first one had an r that was a large number, so our series was increasing in size. The second one had an r that was a small value, which was a half, and we were decreasing in size. So what we want to have a look at is when the absolute value of r is less than 1, and what that means is r is basically between 1 and minus 1. So when r sits between 1 and minus 1, as n goes to infinity, so as we're moving along the terms and we get a massive amount of terms, the successive powers are going to be getting smaller. So r to the n goes to 0. So what that means is the series that we had a look at was, for example, we're at 2, we were at 1, we were at half, we were at a quarter. So our r here is half. It sits between minus 1 and 1. And as we move along until we end up with, for example, half to the 1,000, which is an extremely tiny number. And if you pop that in your calculator, half to 1,000, it's very close to 0. It's such a minute number. So we can see that series would be getting tinier and tinier as r goes to infinity. So the nth term in our series, so a number that's way up the ante, like a half to 1,000, and the sum of that series are going to converge to a limit. Because what we're doing when we're summing way up at the end of this series is we're adding values that are so close to 0 that it won't change our sum. So we're saying that our sum would converge to a particular value and give us a limiting sum. So what we would say would be that for the absolute value of r less than 1, which is the same as r between minus 1 and 1, as n goes to infinity of the terms, the limit as n goes to infinity is ar to the n minus 1, which is our formula on our formula sheet, which is 0. So we're saying that the limit of our terms as n goes to infinity is going to be 0. So our sum, we can say, is going to be given by this formula here, a over 1 minus r. And this formula, actually we might highlight it for you so that you know it's on our formula sheet, and I'll show you in a moment. But this formula here as a limit is saying that, I'll just get my pen fixed up, if we were to expand out the formula that we were using for our sum of a GP, we'd have A times 1, which would give us A minus A times R to the n minus 1. And this A times R to the n minus 1 is going to 0. So we're basically just left with that A and the 1 minus R on the bottom line. And that's where that is coming from. So what we want to do is understand that we're looking at, in this case, the limiting sum of a GP only occurring when our ratio is between minus 1 and 1. If our ratio was bigger than 1, and I've got this crossed out here, but I'll uncross it and we'll fix it up. If the ratio was bigger than 1, or the ratio was less than minus 1, as n went to infinity, the successive terms would get larger. So we might have, for example, 1, 2, 4, 8, 16, and we end up with a term down here of 2 to the 1,000 instead of a half to the 1,000 where we had our example before. We're going to have a massive value. So as we move to infinity, or as our terms get bigger, the term value and the sum diverges. So we're going to have a very large term as the nth term and the n plus 1 term, but the sum is going to be a lot larger because we're adding bigger terms each time. So in this case, I've popped a line through this because that doesn't give us a limiting sum of a GP. It gives us a divergent as opposed to convergent sum. So this formula today is only for ratios between minus 1 and 1. So if we have a look at your formula sheet, first page again under sequences and series, we're now up to that final formula on that sheet. It's written as just S. Normally I like to think of it as sum to infinity, so I'm going to write an infinity sign in there, and it is the limiting sum of a GP. We've got R between 1 and minus 1. So it sits under the GP formulas. It's just for the limiting sum as n goes to infinity, and we get a value that we have as a limit that it tends to. So A over 1 minus R. So that's covering all our sequences in series topics. You can see formula, so we're nearly at the end of this chapter 1. So let's go and have a look at the examples in your book. The first one says, to explain why these series have limiting sums and find them. So we need to decide whether it's a GP or not. So we need to show that. So our first term is 18. It's A. Let's do term 3 over term 2 and see if that's equal to term 2 over term 1. And if so, it's going to be R. So 2, 6 equals 6 on 18, which is equal to 1 over 3, which is R. So it is a GP. So what we have here is, since R is, well, the absolute value of R is less than 1, or we can write it as R is between 1 and minus 1, then we know we can use that the sum to infinity is going to be equal to A over 1 minus R, which is going to be 18 over 1 minus 1/3, which will be equal to 27. So that's a mathematical explanation, but because our R sits between these two values, we're going to end up with a limiting sum, and it's going to go to 27. Let's have a look at B. So again, our first term is going to be 18, and now we're going to look for our R. We're going to test that again as term 3 on term 2 is equal to term 2 on term 1. We always need to test because maybe it's not always going to be that. What have we got here? We've got, okay, 2 on minus 6 is minus 1/3. Minus 6 on 18 is also minus 1/3. So in this case, our R is still between minus 1 and 1. So we're going to have a limiting sum, and it is a GP. It's going to be A on 1 minus R, so it's going to be 18 on 1 minus 1/3, or 1 plus 1/3, which will equal to 27 on 2, or 13.5, and that will be the limiting sum of that series. Let's have a look at 2A here. 2A is a little bit harder. For what values of x does the series 1 plus x minus 2 plus x minus 2 converge? Okay. So when you're looking at that, the word that is going to come to you hopefully there is the word converge. So if we're going to see that word, we're going to be thinking, oh, sum to infinity most likely, but we want to just test that one out. Our first term is going to be 1. Let's just see if there is a ratio that we can use. Term 3 on term 2 is term 2 on term 1. So we're going to have x minus 2 squared on x minus 2. Does that equal x minus 2 on 1? It does, because they cancel out, and we're going to have x minus 2 as our ratio. So it is a GP. We're going to see for what values does it converge. So we're going to be using our sum to infinity formula. So we are going to say if it's converging, that minus 1 must be between, r must be between minus 1 and 1. So what I'm going to do here is pop my x minus 2 between 1 and minus 1. Now, we've looked at solving these before. What I'm going to do is solve it as a whole entire system. I've got minus 2 here. I need to add 2 to both sides. But I'm going to do it here. I'm going to do it here. So I'm going to end up in the middle. And I haven't divided by negative, so my inequalities stay the same. I'm going to have an x. I'm going to have a 3. And I'm going to add minus 1 plus 2. And I'm going to have 1. That's all I actually need to do for that one. They're the values of x. So between between 1 and 3 for my values of x is when my series is going to converge. And that's all it's asking me. So I haven't actually had to work out the sum. But the fact that we're talked about convergence means we're wanting to find that sum to infinity. In part B, it says when the series does converge, what is the limiting sum? So I've tried to do both of them together in there. So sum to infinity is a on 1 minus r. And that's going to be equal to 1, which is my first term, on 1 minus my ratio, which we worked out to be x minus 2. Neatening that up, we get 1 over 1 minus x plus 2, which is 1 over 3 minus x. So my series converges to a limiting sum of 1 over 3 minus x when 1 and 3 are out of bounds of our x. Let's have a look at 3. Find the ratio of a GP. So we've got that it's a GP. We want to find the ratio whose first term is 10 and whose limiting sum is 40. So this one's fairly straightforward. You need to know that limiting sum has a particular formula, and it's a on 1 minus r, and we've got all the other information in here. We know that our limiting sum is 40. We know that a is 10, and 1 minus r is our ratio. So we're just going to use algebra to neaten this up. So I'm going to multiply both sides by 1 minus r to get my 10. I'm going to divide by 40, so I get 1 minus r is 10 over 40. 1 minus r is a quarter. Minus r is a quarter minus 1. So minus r is minus 3/4, which gives me r is equal to 3/4. That's what the question wanted. Just pause the video if you need to go back and work through that yourself. Just moving down a little bit, this is something that might be interesting to note and to understand, that we could also have sigma notation for infinite sums. So again, we're looking for infinite sums here. So our r is between minus 1 and 1, and the GP is going to converge. So the limiting sum, s to infinity, can also be written as an infinite sum. So here is our formula of ar to the n minus 1. And we're saying that as we sum our terms, so this is the formula for the terms on our formula sheet of a GP. So let's just write that in there. That's our t to the n of a GP. And what actually happens when we're working out limiting sums is we're saying as we sum from n equals 1 to infinity of each of our terms, we're going to get a over 1 minus r. So if I pop 1 in here, I'm going to get 1, I'm not going to get 1 in there. When I pop 1 in here, I'm going to get my term A only, because I'm going to have R to the 1 minus 1, which is 0. So I'll just have A. There we are. When I pop 2 in, I'm going to get AR. When I pop 3 in, I'm going to get AR squared, etc. And if we were to individually sum those terms, we're going to get our limiting sum, which is A over 1 minus R. Just something to note, something you may see, and that's, again, only between -1 and 1 for our R.